Welcome. Today we're going to talk about the inscribed angle theorem, but really we're going to talk about strategies for geometric proof generally. This is a diagram of the inscribed angle theorem. Let's talk about what it's about. It's about what happens when we inscribe an angle in a circle. That means that the angle is defined by 3 points A, B, and C, and they all lie on a circle, that is, on the circumference of a circle. So we say that angle A is inscribed, but for that matter, angle B is inscribed and angle C is inscribed as well. So the inscribed angle theorem tells us that the size of the angle A depends only on the points B and C, but not on the specific location of the point A along the circumference here. It tells us in particular that the size of the angle A is half of the central angle that goes across the same chord here. So if the center of the circle is O, then the central angle BOC is going to be exactly double the inscribed angle A, BAC here. So today we're going to see a proof of this, and we're going to talk about how such proofs should work. So in order to do this, we're going to begin by constructing the segment OA. Now, normally we don't even mention something like this. We don't even mention the work of doing it, but I'm trying to be super thorough here. So I'm going to point out the act of actually constructing AO. So that makes the picture look somewhat more symmetrical. And now, in order to continue, we're going to use something like congruent triangles, or we're going to notice that things are equal in length. And so we're going to stare at this picture until we can convince ourselves that we can see that there are patterns here, there are equalities in this length. So let me get out of the way so that you can look at the picture. So where are the length inequalities? Where are the length equalities in this picture? Now, if you're like me and you look for length inequalities, you might see some in various places. AB and AC look to be about the same length. And so it's tempting to say, oh, well, AB is congruent to AC. Let me tentatively write that down just for a minute. So we could say AB equals AC, meaning that those are equal in length. And they do look equal in this picture. But as you can tell here, this is a very generic setup here. We've got points B, A, and C in the circle. On the circle, we've got the circle centered at O. We're not trying to reason particularly about this exact diagram, but any diagram that could be drawn this way. And as you can see here, the point A could potentially be in other places along this circle. And depending on where A is, AB and AC might be equal or they might be unequal. What we're seeing here is that although in my picture, AB and AC look to be approximately equal in length, there's no substantial reason why they have to be. They're not necessarily equal in length, given the setup of this theorem. And so to go on and assert that they are equal is incorrect. They look equal, but they are not necessarily equal in this picture. And this is perhaps the most important thing to remember about reasoning from geometric diagrams. If you're going to reason about a geometric situation, then you're going to need a diagram to help you reason about the geometry. The words and the letters by themselves are not going to cut it. But once you draw a diagram, the diagram can potentially deceive you. You can look at the diagram and you can say, oh, well, my triangle is equilateral. Well, is that a coincidence? Is that just how you drew it? Or is it necessarily so based on the hypotheses of the theorem? So you need to keep carefully attentive to these issues so that you don't jump to conclusions. There are other conclusions in this diagram there are other ways that this diagram can deceive us, and we're going to get to that soon. What else do we see in this diagram? What other lengths look to be equal? OC and OB look to be about equal. Is there any particular reason why OC and OB should be equal? Well, sure. This is the center of the circle, and these are points on the circumference of the circle. So that makes this a radius, and that makes this a radius. And for that matter, this is a radius too. And so all of these are equal. So let's assert that OA equals OB equals OC. Now this equality, of course, is an equality of length, not an equality of identity. It does not make any sense to say that OA and OB are identical. They are certainly not identical in the sense of being the same segment, having the same location, having the same endpoints. This equality is an equality of length. They have the same measure. We'll also write equalities of angles in the same way, not meaning that they are identical angles, but meaning that they have the same measure. Okay, so if we're going to assert some equalities, then we should have a reason. And this is because they are radii. Radii, of course, not just radii of different circles, but of course radii of the same circle. So we get those inequalities. those equalities. If we have those things, then we have various triangles in this picture that are isosceles. So let's point them out here. So triangle ABO and triangle BCO and triangle CAO are all isosceles. And for the record, what does isosceles mean? Because this causes some confusion too. So isosceles means two or more equal length segments. That's not a completely rigorous definition because I'm not saying it is a triangle having these properties. But the point that I'm trying to make here is that, first of all, isosceles by definition makes no claim about the angles in the triangle. It is merely a statement about the lengths of some of the sides of the triangle. Furthermore, isosceles claims that two lengths are equal. It does not claim that the third length is unequal. So an equilateral triangle is technically isosceles as well, in the same way that a square is technically a rectangle as well. These definitions tend to be inclusive of their own special cases. And it tends to matter. It tends to make a difference in the theory, whether we do these things this way or not. Now, so why are these isosceles? Because each of them has two of these segments that I claimed are equal. So what do we know about isosceles triangles? We know that isosceles triangles have equal base angles. Do we know that? Well, probably you're familiar with this and probably you've heard of this. I'm going to state this as a theorem, and then so we can talk about how much we know it. So if I'm going to state this in terms of a generic triangle ABC, if triangle ABC has, and now I want to say specifically, AB equals AC. So it's isosceles, but not just any legs equal, but those in particular, the legs that land at A are equal. Then angle B is going to equal angle C. And to illustrate the picture, let me draw an isosceles triangle. It would help if the one that I drew were, in fact, isosceles. So here's A, here's B, here's C. Here are a couple of equal sides. And then this theorem says, then the base angles are equal as well. Base angles of isosceles triangles are equal. I want to remind you, and this will come up again later in the course, every triangle has a base. But it's not true that it has just one base. Any leg of any triangle can be regarded to be the base. Every triangle has three bases and three heights. It all depends on how you look at that triangle. In any event, we have this theorem that isosceles triangles have equal base angles. Now, we're about to use this theorem in the continuance of this proof. I don't want to get distracted from this proof, but I need that theorem stated so that I can use it here. There's something else that we should be concerned about. We should be concerned about getting our ducks in a row here so that we know what we're using and we know what we're proving with it. But we should also be concerned about making sure that everything that we're using, we have responsibly learned. And to responsibly learn a theory at this level, a theorem at this level of undergraduate geometry, we need to know its proof. And so I want to remind you here that there is a proof of this theorem, the one that I'm about to invoke. There is a proof of this theorem. You deserve a proof of this theorem. You should demand a proof of this theorem, but I don't want to be doing two things at once, right? I'm in the middle of this proof. So this is important. Knowing the proof of this is important too, and that's in a separate video. But I don't want to distract from the theme here. Let's return to this theorem. We know that AB, AC, and OB, OC, and OA are all congruent. We know that each of these smaller inner triangles is isosceles, and so we get equal base angles for those triangles. So what does this mean in our cases? This means that OBC equals OCB. So we get angle OBC equals angle OCB. That is, this one and this one are equal. And so we get angle OAB equals angle OBA. And let me simply say, etc. And once we identify that those base angles of the three isosceles triangles are equal, then we can give them some names. And so what I'm going to do is I'm going to label them with unknowns. I don't know the angles, I just know that they're equal. But since I know, for example, that this angle is equal to this angle, then I can give them the same label. So I'm going to label this x because I don't know its value. I can't possibly know its value, not generically, because this diagram represents millions of diagrams that might look similar but are different. So I don't know the size of this angle, and I don't know the size of this angle, but I do know that they are the same, and so I'll label them both x. Then similarly, I don't know this angle, and I don't know this angle, but I do know that they agree, and so I'll label that y. And ditto here, I don't know these angles, but I know that they agree, and so I'll call them z. Now we might be tempted to say things like, well, we might be tempted to say, perhaps in red, we might be tempted to say y equals z, because if you look, hey, look, they look like they're pretty much the same. And sure, they do look like they're pretty much the same. And sure, in my picture, they are pretty much the same. And this is probably close to true in my picture. But this is another coincidence of the diagram that I've drawn, which is not necessary based on the data that's in the theorem. And you can tell the difference because there's no particular proof theoretic reason why y should be equal to z in this diagram or this problem. We won't be able to justify it, in other words, right? We can justify this because they're equal base angles of isosceles triangles, but we can't justify the claim that y equals z because it's not a necessary feature of this scenario. There's no particular reason why it has to happen that way. I want to justify this prior claim that the angles are equal. So this is by equal base angles of isosceles triangles. If I could spell isosceles, that would help, of isosceles triangles. So that's a justification for this claim of equality here, and that's the justification for this label. And what can we do next? Well, I want you to, now we've thought about this isosceles triangle and this one and this one. Now let's think about the exterior triangle ABC. That triangle has all of its angles effectively labeled in terms of the unknowns x, y, and z. And so now we can reason about what happens when we add all of these things up. So angle A is y plus z, angle C is x plus y, angle B is x plus z. And when we add them all up, we should get 180. So let's record that. So y plus z plus x plus y is equal to 180. And this is because the sum of the angles in any triangle is 180. So again, this is a fact that you should know about prior knowledge geometry, that when you add up the angles in any triangle, you get 180. And it's a fact that I'm using here with proper citation in this proof. But that doesn't mean that it's just, you know, everybody knows. It doesn't mean that it's just folklore and you should just depend on it. And it doesn't mean that because I say it's true, you should believe it. It is an important fact and you need to know it, but you also deserve a proof of it. So let's put it over here with our prior knowledge theorems. So the angle sum, I'm going to sort of abbreviate it. The angle sum in a triangle is 180 degrees. It doesn't really matter that it's exactly 180 of something because the degree measure is somewhat arbitrary. What really matters is that it's equal to a straight angle. The angle made by at a single point on a straight line. So double a right angle. So the angle sum in a triangle is 180 degrees. And again, I'm going to indicate that there is a proof and there has to be a proof. And you should question what is the proof, and you should be concerned about that, right? That's not something that we should simply neglect, and it's not something that we should just take for granted. These proofs matter. They just don't fit in the same conversation with this proof. So what's happening here is we're developing this proof, and we're saying, oh, there's actually a lot of prior knowledge that we need to get in order so that this proof can work. But not to distract from it, I'm not going to go into that proof now. I just wanted to go on a list of things that hopefully you will demand from me later. Okay, so let's return to this. We have this situation. So 2x plus 2y plus 2z equals 180. I'm just algebraically simplifying this sum. And it's tempting to divide by 2, but it's not actually helpful right now. So are there any other, well, I mean, we haven't done it, right? What are we trying to do? We're trying to show that angle BAC is half of angle BOC. Now, angle BAC is y plus z. So maybe we should think about y plus z here. I don't know. And we need to think about angle BOC. The thing about this proof so far is we haven't really focused any of our attention specifically on angle BOC, which is right here. Now, one thing you could say is you could say angle, let me switch color for this, not to deceive anybody. One thing you could say about angle BOC, you could say that it's a right angle. And sure, it does look like a right angle in my picture, but hopefully you're getting this theme, right? It looks like a right angle in this picture because of the particular positions of B and C, but this is just one of many, many pictures that could exist, and there's no particular reason why it had to be a right angle. Move point C a little bit over this way, a little bit over this way, that angle will change. There's no essential reason why it has to be that. It's not necessarily a right angle. And so any attempt to conclude in this diagram that BOC is a right angle is going to be wrong. I cannot possibly justify that. It's not a necessary conclusion. Even if it's true of my picture, it's not true of all possible pictures. This is the thing about geometry, and I'm trying to make that the sort of the secondary theme of this proof. You have to reason from a picture, but at the same time, you have to not let the picture deceive you about what you're trying to accomplish. The picture necessarily has coincidences in it. It necessarily is a special case. It necessarily has particular details that are not the same as the way that it will always be. And you need to be careful to distinguish, do I really have a necessary reason for this conclusion? Or am I just recognizing something that's accidental in the picture that I've drawn to help me think about it? So one of the ways that it helps me to think about whether this is an accident or a necessary condition is to think about how much can I move these things? The picture could be, the circle could be smaller or larger. The point B could shift over a little bit. Which of these things will no longer be true if the points move a little bit, right? I will certainly get a Z and an X, but they will be slightly different. This angle might not be a right angle. That's one way to help you think about it. In any event, I was saying we need to reason about BOC because it's in the conclusion, and none of the work that we've done specifically helps us reason about BOC. And recognizing that it's a right angle is certainly not going to happen. So what can we say that is specific to the angle BOC? Well, so that's this angle here. Not much, except that it is in a triangle, and the triangle is triangle BOC. And so we could say something. We could say this thing all over again. And so let's do that. So angle BOC plus x is likewise equal to 180 degrees. And now it certainly is a happy feeling when I have two equations, right? Especially two equations involving some of the same unknowns, because now I can just perform algebra on these equations. And I can do all kinds of things. I could set them equal to each other. There are all kinds of ways of thinking about what happens next. Probably the simplest thing to do is to take this, which equals 180, and this, which equals 180, and set them equal to one another. What happens when we do that? We get 2x plus 2y plus 2z is equal to angle BOC plus 2x. Oops, I wrote that wrong. BOC plus 2x. Okay, so that's fun. What else can we do? We can cancel the 2x. 2y plus 2z equals angle BOC. And then I suppose we could factor out the 2 and divide by 2, and we would get y plus z is 1/2 of angle BOC. So here I'm just fooling around with algebra, just seeing where the algebra takes us. No particular direction in mind, no particular conclusion in mind, but oops, I accidentally proved the theorem because y plus z is exactly angle A here. So to be specific, that's angle BAC, and I just proved that that's half of angle BOC. So here we see the conclusion that angle BAC is exactly half of angle BOC as desired. And if we want to prove that we've had a college geometry course and know how to end a proof, we can say QED if we want. Or is it? So are we done or are we not? Well, we are done in a sense. We have proven the conclusion, right? We took B and A and C, and we've demonstrated here by solid logic that angle BAC was half of angle BOC. But I want to sort of end this lesson with some warnings and some what ifs. And it all goes with the theme of let's not allow the diagram that we draw to confuse us about the proper conclusion. Let's not let the diagram that we draw deceive us about what is actually happening when we inscribe an angle BAC in a circle. And so let me suggest how we may have accidentally deceived ourselves after all. So this is right in and of itself. There's nothing wrong with this. Everything here is correct. Everything here is necessary, but it may be incomplete. And the reason it may be incomplete is that this diagram may have deceived us after all. Because one of the things that happened in this diagram is that this diagram convinced us that the point O is inside the triangle ABC. And you might say, well, yeah, obviously the point O is inside the triangle ABC. And well, okay, yes, it is obviously inside that triangle. It is not on the edge. It's not on one of the edges, AB or BC or AC. It's certainly not external to the triangle. And this mattered, right? Because we put it in the middle and then we subdivided the original triangle ABC into 3 smaller triangles, which were part of it. Is that a necessary circumstance? Is it truly necessary in the setup for this theorem that O is inside ABC? Well, BAC are just points on a circle, and O is just the center of the circle. That's all we have in this hypothesis. The diagram is not the theorem. The diagram is not the hypothesis of the theorem. The statement here is the hypothesis of the theorem, which guarantees only that points B, A, and C are all inscribed in a circle. And that O is its center. So those are the only hypotheses. These points could have landed anywhere along the circle. And so let's look at what might have happened differently. So I'm going to focus on what happens for the moment if I move the point A. I can't put it here because I drew my circle too big and it'll go off the board. But point A could have been here. There was no rule that kept point A from landing there. And if point A had been there, then a peculiar thing would have happened. The point O, which is the center of the circle, would not have been interior to the triangle. It would have been it would have been on the edge AC. And then B could have been like right here in the middle, making what looks like 2 right triangles, but it might not be, right? B could be here, in which case we'd get something quite a bit more lopsided. So that could have happened. Now, does it matter? Well, it matters if you, well, does it matter or not? The question about whether we should be concerned, should we have a special concern for this situation? It boils down to, in this situation, can we or can't we read exactly this work and make sense of it? If this work actually makes perfect sense about this, then we're good to go. And if it doesn't, then we have a problem and we need to consider a special case. So let's read it. Construct OA. That's already a strange statement, right? But okay, I'll construct OA, even though sort of unnecessarily. Then OA equals OB equals OC because they're radio. That is still true, still correct, no problem. Okay, so now I have 3 isosceles triangles. OBC, so ABO, BCO, and CAO are isosceles triangles. Now let's look. ABO is indeed isosceles because these two lengths are equal, and it follows that these two are equal angles. BOC is indeed isosceles, and it's the same length, so I'll just use it this way. And that makes these things equal. That makes that isosceles. But there's a further claim here that CAO is an isosceles triangle. And maybe by some stretch of imagination, you could try to convince yourself that CAO is some sort of trivialized isosceles triangle, but really it's not. It's not a triangle. Those points are collinear, and they do not form a triangle. And that means that this proof is wrong, doesn't apply to this situation. Something else has to happen. Now, is it a big deal? Well, yes and no. It's not a big deal in the sense that the new thing that has to happen is pretty similar and not any harder to do. But it is a big deal in that the proof we tried to write was wrong, right? I mean, it was correct for the special case that we got, but it was incorrect for another special case. And so this is the other thing that makes geometry hard, right? You draw the diagram and you try not to be deceived by the diagram. It's not just the special lengths and special angles in the diagram that can confuse you, but it's the basic structural arrangement of the points. The diagram that I had originally convinced you that A, O, and C were non-collinear because, well, there they are, non-collinear, making a triangle. But now you see this diagram was possible as well. They could have been collinear. Other things can go wrong in this diagram. Maybe A, O, and C are not in a line, but maybe B and C are in a line, right? I guess I could have left the line here. So maybe B is in a line with O and A is not. And you might say, well, that's the same case. But I would say, no, it's not the same case because I am particularly trying to reason about the angle made at A. And so here, this is like A has a different relationship to this collinearity problem. So this is actually a different special case where B and C are collinear that needs to be dealt with separately. And if you read through this proof carefully, it refers to triangle BOC or BCO here being isosceles, which is incorrect. And so a different kind of reasoning needs to be applied there. Now, it's not hard. Again, we make not 3, but 2 isosceles triangles. And we reason about their angles, and then we reason about the larger triangle, and then we get it. But the point is, it's a special case, and it really does need a slightly different treatment. Things get even stranger, right? So what if instead of the collinearity problem, we have a different arrangement, a different relationship to the point O? So in the original picture, I had B here, I had A somewhere up here, and I had C here, and there was O. This was the original picture, and when I drew ABC, O was on its interior. But this is not necessary at all. A could be here. And if I draw A here, then I certainly can have a triangle ABC, and I do end up with an inscribed angle A. But now everything goes a little bit haywire, right? So yes, I still have segments OC, OB, OA. Yes, all those segments are radii, so they're equal. If you read this line is still true, actually. In this situation where O is external to the triangle, I really do still have 3 isosceles triangles, and they really are the ones claimed. So ABO in this situation, ABO is isosceles, sure enough. BCO is an isosceles triangle. And CAO is an isosceles triangle. So this line seems okay. And then all of these things, are those still true? Well, these things are still true. You can check them. But this is now kind of a problem, right? Because now the labels that I've placed on X and Y and Z, it's not quite clear how they should be labeled. And the problem here is that these 3 triangles, which are isosceles, are no longer portions of the original triangle ABC, right? The original triangle ABC is here, and the angles within it are not the sums of the various angles made with O, because O is not inside it. And that means that when we try to apply the angle sum equals 180 thing to the triangle ABC, something goes wrong. Is it fixable? Yes, of course it's fixable, but it's different. And so this is just another illustration of how the diagram has many options, and there are many ways that you can deceive yourself about what is the necessary consequence of these arrangements of points on a circle. There are many cases, and many cases have to be considered. So just to lead up to some upcoming homework here, on your homework, what you're going to be doing is taking 1 or 2 of these cases and proving that, well, adapting the proof to one of the other special cases, including one like this, and seeing that it works anyway.